Section 6.6 Calculating the Gibbs energy of mixing for ideal gases. Assume the initial temperature and pressure of each ideal gas are the same before mixing, and then Gibbs energy of mixing is simply nRT times the sum of xi times Ln(xi). So if you have three gases, their number of moles are, let's say, 2, 3, and 5. And then the mole fractions are 0.2, 0.3, and 0.5. You simply plug in these numbers and get the sum. It's going to be a negative number. And then multiply by nRT. N is 10 moles. That's the total number of moles. 2 plus 3 plus 5, that's 10 moles, times R times T. You get this Gibbs energy of mixing. It's negative because mixing is spontaneous under this constant temperature and pressure condition. How do we compute the entropy of mixing? Well, because dG equals negative SdT plus VdP. And then pressure is constant. So dG is equal to negative SdT. So delta G over delta T is negative entropy. So entropy is negative delta G over delta T. And now we simply use that equation. Entropy equals negative dG over dt under constant pressure for two scenarios: before mixing, after mixing. And then we take the difference. And then we get the entropy of mixing is simply negative the first derivative of delta G with respect to temperature, again under constant pressure condition. So you can just plug in this expression of delta G mixing here, and you will see the result is simply negative nR times the sum of xi times Ln(xi). So look at these two expressions. Delta S mixing, delta G mixing. They differ by a factor of negative T. So this entropy of mixing is always greater than 0 because this sum is always negative, and we have one negative sign here. How about the entropy of mixing? It's 0. Well, it's simple. You simply just do delta G plus delta Ts, and you plug in this for delta G, plug in this for delta S. The result is 0. What about the internal energy of mixing? Well, it's definitely 0 because, again, we're talking about ideal gases. The mixing does not change the potential energy. It's always 0. It does not change the kinetic energy as well because we assume there is no temperature change. Therefore, there's no kinetic energy change. The mixing of ideal gases does not change the internal energy or enthalpy. However, the entropy increases. The Gibbs energy decreases. Now let's look at one numerical example. Let's mix two gases, A and B. Let's say we have 1 mole A, 4 moles of B. Then the mole fraction of A in the mixture is 0.2. The mole fraction of B is 0.8. The total number of moles is 1 plus 4. That's 5. R, temperature T, and then the sum of X times Ln(x) right here. Only two species. Therefore, only 2 terms here. The result is negative 6.24 kilojoule. This is how much the Gibbs energy decreases after mixing. What about the entropy of mixing? Well, the entropy of mixing is simply this delta G mixing over negative T. And then this is a positive number. Pay attention here. This is joule, not kilojoule. It's 20.8 joule per Kelvin. What about the volume? The total volume remains unchanged after the mixing of ideal gases. We can prove that because dG equals negative SdT plus VdP. If we look at the constant temperature condition, volume is simply dG over dP. And then delta V is simply the first derivative of delta G with respect to P. So we go from here to here by applying this equation to the initial state, that's before mixing, and to the final state, that's after mixing. And then we take the difference. We got this. And pay attention, because this delta G mixing does not depend on pressure. Therefore, this is 0. Therefore, the volume change after mixing is 0. So you start from a total volume of, let's say, 20 liters. You end up with 20 liters. And then we can easily prove this delta H mixing is 0, and also delta U mixing is 0. So this is another way to prove delta U of mixing is 0, because if delta H is 0 and the temperature is constant, therefore P times V remains unchanged. So this change is 0 as well.